Hello, this is Tierney from Monroe Community College, and we're going to start a series of videos about polarity, both within bonds and within molecules. This video we're going to be talking about electronegativity and polarity of bonds. So what is electronegativity? I abbreviate it as capital EN. And what it is it's the relative ability of a bonded atom to attract the shared electrons. So here I have two covalent bonds illustrated for you. The covalent bond between two hydrogen atoms and the covalent bond between a hydrogen and a chlorine atom. In the first bond, since both atoms are of the same element, they share the same ability to attract the shared electrons. They have the same electronegativity. So those electrons are going to be shared evenly. If we look at the second bond between hydrogen and chlorine, chlorine actually has an ability to draw those shared electrons towards it more than hydrogen can. We say it has a greater electronegativity, and it gives us what's called a polar bond. I want to look at how we decide which atom has a higher electronegativity. So if we look at our periodic table, I have here listed the values of electronegativity for all of our elements. If you notice, we do not have values for the noble gases. That's because they do not tend to bond, so we don't assign them electronegativity values. So if you take a look within a group, so let's just look at the first group, we see that the value tends to drop as we go down the group. This is because our value of N, our number of shells, is increasing. So let's just draw an arrow down this way. Because our number of shells are increasing, the electrons that are being shared, the valence electrons, are further and further from the nucleus. The nucleus is what draws those electrons in when they're bonding. So if you have electrons that are very far from the nucleus, they are not as attracted. So within a group, as N goes up, our electronegativity goes down. This also means as the atomic size goes up, our electronegativity goes down. Now within a period, as we go across, that electronegativity increases. This is because the effective nuclear charge is also increasing. A discussion of the effective nuclear charge was given in a previous lecture when we talked about periodic trends. And we know that as we go across, we are increasing our effective nuclear charge. And what this charge does is it draws in those valence electrons because we're getting increasing positive charge that the valence electrons feel. So across the period, as our Z, our atomic number, goes up, our electronegativity goes up because of that increase in effective nuclear charge. So electronegativity really is a measure of how the nucleus draws those valence electrons closer to an atom. Now let's take a look at how electronegativity affects individual bonds. So when you have two atoms of very similar or equal electronegativity, like the first structure we see here, a covalent bond between two hydrogen atoms, you get an equal sharing of electrons. This means that the electrons effectively hang out between both atoms equally. We have what's called an even electron cloud. An electron cloud tracks where the electrons are located. And if we were to draw that, the electrons would mostly be located between the two atoms and would spend an equal amount of time around each atom. If we take a look at a polar covalent bond, this is a bond between two atoms of unequal electronegativity. If we take a look at the electronegativities we see, so let's go back, hydrogen has a 2.1 while chlorine has a 3.0. So chlorine is more electronegative than hydrogen, and so these two electrons are going to spend a little more time by chlorine, as I've shown in the picture. And our electron cloud is going to be significantly bigger by that atom with the more electronegative value. This is called a distorted electron cloud because the side near the more electronegative atom is going to be bigger because the electrons spend more time by the more electronegative atom. This leads to partial charges, not full charges like we see in ions, but partial charges. where there's a partial negative charge by the more electronegative atom. We call this the negative pole of the bond. And there's a partial positive charge by the less electronegative atom. We call this the positive pole. We can denote these poles in two different ways. We can use arrows or deltas. I'm going to show you both of these denotations. In class, we are going to be using the arrows more commonly. So if we take a look at the HCl bond, we know that the more positive area is going to be by the less electronegative atom H. So we draw an arrow to show the electrons hanging out by the more electronegative atom. So that arrow shows the electrons moving towards the chlorine, and we put a plus at the end of the arrow by the positive pole. So we just draw an arrow pointing towards the more electronegative atom with a plus at the other side, and we draw that in the vicinity of the bond. We can also draw it using deltas. This is a lowercase Greek letter, and if you draw it like an 8 that you haven't completed, like that works for me. That's how I draw them. This means partial, by the way. So we draw a delta negative in the vicinity of the more electronegative atom, and we draw a delta positive near the less electronegative atom. So what we get is a continuum of the types of bonding that we've discussed in this class, where we move from a nonpolar covalent all the way up to ionic bonding, depending on the differences in electronegativity between the two atoms. So let's review what we've talked about. A nonpolar covalent bond is going to have equal sharing of electrons, and you're going to have an even electron cloud. So I'm just going to draw a very even electron cloud, showing that the electrons spend equal amounts of time by both atoms involved. A polar covalent bond has what's called a partial transfer. I'm not even comfortable using the word transfer. I would say unequal sharing. I know I wrote that, but I like this better. Unequal sharing, where the more electronegative atom is going to have a distorted, bigger part of our electron cloud. The electrons spend more time near that more electronegative atom, but they're still sharing the electrons. The electrons still will be near the hydrogen sometimes, just not as often as near the chlorine. When we have a bigger difference, a very large difference in electronegativity, you get a complete transfer of electrons. So basically, your sodium's electron hops over to the chlorine, and the chlorine gains a negative charge, while our sodium gains a positive charge, a complete charge. That happens when you have a great difference in electronegativities. This happens when you have a metal bonding with a nonmetal. So if you notice, all of the metals have fairly small electronegativities, while all of the nonmetals have greater electronegativities. So when you have a metal bonding with a nonmetal, the difference is great enough to result in a complete transfer of electrons. So now that we've talked about polarity of bonds, we're going to apply this to whole molecules in the next video. So I will see you in that next video.